Hello, everyone, and I welcome you all to another meeting we have here on the Computer Vision Group with Cohere for AI. Today, we are going to be listening to Diganta Misra. He is a machine learning engineer focused on the research area. He does research in machine learning, and his main job is, just main research in machine learning, where he does a bunch of research in generative AI, basically generating data via generative AI techniques. He is the co-founder of Landskape AI, and he works as a research engineer at the University of Carnegie Mellon. He also has a fellowship. He's working on a fellowship at the Max Planck Institute in Tübingen. I think he began there quite recently, if I'm not mistaken. So without further ado, I think it's time we turn the mic over to Digant and let's hear what he has for us today. So over to you, Digant. Nice having you here with us.
Okay, great. Thank you. Just making sure that I'm audible and you can see my screen.
Yes.
Okay, perfect. Okay. All right. So, hi everyone. Yeah, I'm Diganta. So today, I will be talking about the whole paradigm of synthetic data, and then focusing on a work of mine, and it will be around computer vision and generative data, of course. But the concepts presented are sort of agnostic to the modalities and can be most likely extended to other modalities if you're coming from a different background and not computer vision. So I'll try to make it as interactive as possible. If you have any questions, comments, feel free to interrupt me, ask it out during the session. Happy to answer them. um, okay, so let's start with a quick eye test. If you have attended a talk of mine like this before, um, you might have seen this, but if you haven't, that's good for you. Is This is just a refresher to start with. So um, for everyone present, I just want you to, in the chat, write which of these do you perceive to be generated. There are generated image in this slide, so I just want to see um, whether people are all on the same page. um, so yeah, like, just write out the names of whoever you perceive is not a real person and is a generated image, and I'm happy to sort of see the chat and see if we're getting it right. So we have like three options: Charlie, Ravi, and Carl. Uh, Carl and Charlie seem generated. Okay. Right, so Carl. Okay, so all of them. Okay, so I'll maybe like give like a last glance at this, if it's still not on the same page. Um, any other response? No. Okay. Well, maybe this was more straightforward than I imagined. Um, so yeah, Carl and Charlie are generated. Although I feel like maybe it was not the easiest. Um, One of you did say all of them are generated. That's incorrect. One of you just A few of you said only Carl is generated, which is correct, but also Charlie is generated. I feel like out of all, if I were to pick one, I would have just picked Charlie, and I would have argued that Carl and Ravi are real images. But um, yeah, like the point being that we are at a point in time where generated images, especially of people or other well articulated and understood subjects, are becoming so photorealistic that it is becoming really hard to distinguish, like images from actual photographs to that of generated images. And maybe this was a easier eye test, but if I would have changed this to artwork, right, and I would have asked you which one do you conceive to be real artwork versus generated artwork, I feel like that would have been very tough for a average human, especially for someone who probably does not have background in formal arts. Then it would have been really tough. But the point being that earlier we didn't have to look twice to say whether it was generated or not. Now we have to look very closely. We have to look at artifacts, we have to look at minute details in the images to have any confidence in saying whether it is generated or not. Um, and I got this quote from Chat GPT, that like when were 3 or 4 years ago in the space of deep learning, and GPT was in its infancy, and other strong models, even in vision, where like resonance transformers were just getting off the ground. Every The whole talk of the town was about models. Everybody cared about the architecture, the design of the architecture, or rather the mechanism that was underlying the training process. And usually nobody looked at the data. I mean, we all understood the importance of the data, but we all took it in some sense for granted, because we assume that we have these data sets available, especially like ImageNet, and which was still very relevant, at least 4 years ago. Um, and we never considered going outside of that worldview and considering that data has a much more significant role to play in the training process of these models. And now that we have sort of plateaued at a stable design of architecture, preferably transformers, that we understand scales very well in terms of hardware, we are now focusing a bit more on the data. And that is to no surprise, because um, data dictates the performance that we can derive out of these models. You can have as good a model in terms of design, as stable as it can be in terms of training mechanism, but if you just lack the appropriate and the clean balanced data to train on, it doesn't like the end result out of it would be suboptimal. Um, so the goal of this talk would be to sort of give you the overview of why data is so important, and while people say that data is abundant, it is actually not the case. Data is quite scarce, and finding the right data and the um, clean data is in fact even more challenging. Um, and again, this talk will focus on generative approaches. So I want to convince you that um, generative data is at a point where we are at right now is very reliable to be used in training these models. You might think, oh, this is all, coming back in the same cycle, like, because we train these generative models on real data. So they are a limited worldview of what we have shown to them. Yes, however, the range of extrapolation and capabilities of doing multi concept generation of these generative models is really remarkable at this point. Like, for example, you might not see certain concepts together in the natural world, but you can for sure most likely generate a very realistic or artistic rendering of that prompt per se through a generative model today. And yeah, we have come like a pretty long way from where we started out. I'm sure people who are coming from a computer vision background and have taken some sort of a computer vision 101 course must have started out with these lectures about CNNs, and then would have gone to VAEs and then DC GANs. I remember myself like studying DC GANs and how to use them for MNIST generation and eigenfaces. So yeah, so the evolution of generative models have been quite significant and quite drastic. Modern generators like DALI, Stable Diffusion, or other competitors out there are just so good in terms of rendering images that you'd be surprised that the three candidate images that I used in the eye test, they're from SDXL, which is like a few years old now. Like, guess that's 2.5 or around 2 years old. So uh, and that's not even the state of the art model. So it's quite remarkable that a model of that capacity and of that shelf life can do so well in today's day. So as I was saying, we can now generate images of people, images of landscapes, images of concepts that we would never ever see in the wild. Like, you would never see a fox having popcorn in a cinema. But yeah, we can generate them, and we can generate them because these models have a very compact, unified representation of concepts that they are exposed to during training. Um, so there is a very blurry line right now between human imagination and generative modeling, because like some of these images that you see might be your first rendering in your thought if you were given the same prompt. So I would say like generative models are coming close to a point where they can articulate the human visual thinking process when given a particular prompt. And this is not me trying to argue in its favor. Companies like big tech firms are putting a lot of emphasis, money, resources, personal um, on this domain. There's Google, Runways, Pika, Meta, Apple, Stability. Like, there are like countless of them. These are like probably the top dogs in the industry who have like generative tag in their MVP. But um, if you look outside of the big tech, you look at individual smaller startups and firms that are having very niche products which rely on generative models, countless of them. So I don't have to convince you that the industry agrees that this is a very important domain and field, and one that is growing impressively fast. So where I want to take this is I want to shift the paradigm of training, especially in computer vision, from the supervised approaches to generative supervised training. What do I mean by that? So there are quite a few works that have come out recently. I'm pretty sure some of these have been seen by a few of the people in the audience. Uh, all these works revolve around how can we incorporate generated data uh, into our training process as training data. It might be standalone generated data, or it might be coupled with the real data set. There are different objectives for this. Like, you might think one objective is to balance imbalanced or long tailed data set in the real domain. So if you have um, way higher number of images for certain classes as compared to some other classes, you might want to increase the tail classes by generating data for them. Or you might just want to increase the volume of the whole data set, or you might want to add concepts. So there are different objectives. But all these papers, like I showed two papers in this slide, um, and there's another work here. All these papers try to incorporate the notion of generated data into the training process and show that it helps in performance improvement, and not just in standard, supervised, like classification settings, but also in, like this slide shows, in multitask setting, in vision language setting, um, and also in audio and offline reinforcement learning. So as I said, most of the stuff that I'll touch upon is modality agnostic. It doesn't have to be restricted to computer vision. So these applications of generated data is definitely uh, open to be used for domains like audio or video or reinforcement learning, and different tasks as well. But the current talk of the town in terms of what matters in research, or even from a production perspective, is whether any given technique or improvement is scalable. So the same question applies to generated data. Does it scale? Like, does it scale well in terms of compute and performance trade-off? The answer is a mixed bag. So there is a paper that derives the scaling laws for synthetic images based model training, again for um, training like clip models. So it's not like universal synthetic images training. Like, there can be various other approaches to train with synthetic images, but take this as a sort of a reference. And while they show some improvement, um, like in terms of, getting better OD robustness to certain out of domain tasks, they sort of argue that synthetic data is sort of slightly worse than that of real data for clip training. um, I feel like there is a lot of ifs and buts to derive from this conclusion that they come to in this work, because there is a lot of assumptions that they take. For example, they they rely on a single generator, they rely on a fixed set of prompt templates, they have they have a very single straightforward generation process, and all of this contributes quite heavily, as we will show in the later slides, of how generated data can scale. So while there is a paper that tries to answer the question that I posed before, I would argue, from my own intuition and from reading this paper, is that take this conclusion with a pinch of salt. Yes, the observations are accurate, but they are not truthful to answering the question in a very concrete manner. Okay, so this was sort of the prelude of my talk. I'd now go into the specific paper that I want to discuss. So this paper has been out for a while as a preprint on archive. The paper is called, just say the name, Online Continual Learning with Category Names Only via Data Generation. I just want to give a quick heads up about this paper, being that there is a follow up work that uh, will be coming soon, not as a separate paper, but just as a revised version of this paper, which significantly changes some of the design elements that we had in this paper, and subsequently also the results, drastically improving it. I'll try to highlight which parts are changed so that you are well informed that we have taken it into consideration, because it is not out yet and I don't have any specific slides to show you that right now. But yeah, just to let you know, and this work is in joint collaboration with some students and professor from South Korea at Yonsei University and Seoul National University. Okay, so let's give a quick background. So as you know, that most of the current data sets that you rely on, or you must have already tried if you have trained a model before, are either manually annotated or web script. So what is the difference between the two? Manually annotated means that you have this, like, you have a folder, you have the name of the folder that represents the class of the image, and inside that folder you have images, right? So you know what each image is, which class each image is belonging to. Makes your life easier, because by the very definition of the term manually annotated, it means that humans have done it, right? So you sort of have this trust that, yeah, this is clean data, it has been processed, and it's ready to use. But while that might all sound good, there are limitations to manually annotated data sets, which are more on the axis of controllability. So you cannot control it. You cannot control the diversity or the type of images, or basically, you cannot control any aspect of the data set. It's a data set that has been concretely finalized, provided to you. You just use it. You can change aspects of it by doing augmentation and other um, you know uh, photographic editing, but the actual images is what you'll rely on, and you do not have any control over it. You obviously have storage issues. We are in a timeline where storage is rather trivial, like we can store terabytes of data quite easily. So this is in paper an issue, but not practically that much relevant. However, manually annotated datasets have very limited, if not any, usage restrictions and privacy issues, because they have been constructed with that in mind, that people will be using it to train the models. Just like if you have trained on ImageNet, you have gone to the ImageNet official website, you have to agree to the terms and terms and conditions about the usage policy of the dataset. But once you have formalized yourself with the um, TOS, then you should be able to use it to train any model, right? And usually, because these data sets are constructed with model training in mind, the noise level, in the sense that the images that will encounter noise in any definition of noise is quite low. But because this involves so much of manual effort, the acquisition cost is accordingly very high. So if you were to, collect a million images and then do mechanical turk and annotate all of them by five workers and then take the average label, that's going to cost you a lot of money. Um, so there are some drawbacks to manual annotation. But then you look at the other end of the spectrum, which is web scraping, and life gets a little bit easier in that case, right? So you have heard of the Lion data set, you might have heard of CC data sets. These are all web scrape data sets. So controllability is sort of a meh in that, because you are at the mercy of what is put on the internet. So it is of course more diverse. Like you can at this point go to any search engine and type a prompt, as unnatural as it might be, you still will encounter some images, even if it is not exactly true to the caption that you're typing, but you'll still have search results. You don't have any storage issues because you can crawl on the fly. You don't have to explicitly store this data like the search engines. They do it for you essentially. However, you have heavy restrictions in terms of usage and privacy. And why is that the case? Like I think if you I'm very certain that you guys have seen, when you do Google image search, there is an option in the advanced search about image rights, usage rights, and you can filter by Creative Commons or some other options, if I remember correctly. I don't know if people have seen it or not, but that is essentially a big no-no in web scraping. That like there are images on the web that should not and more likely cannot be used for model training. And same goes for privacy, because the images of real people, actual event that people are sensitive to, be used for model training or be disclosed to the public. But on the contrary to manual annotation, the acquisition cost is super low, because I mean, you don't have to do any labeling, because the label is itself the caption that you're using to search these images on the web. Itself you are labeling it, but not individually. But the noise is pretty high, and I'll show you some actual noisy web samples. But it should be pretty obvious why the noise is high, right? It's the web. It's a collective brain dump of the entire human civilization, and we are very noisy social beings. So we don't tend to agree on every concept's representation equally. So some of these images might be very, very drastically different than the average image that you might expect for a certain prompt, and you might have other kind of noise like watermarks or yeah, just perturbation. Then you have generated data, which sort of ticks the green box in every single regard, in my opinion. It is controllable. What I mean by that, you want any specific concept in combination with any other concept, you got it. Like, ask for a cat playing soccer, possible, right? And extensively possible with different themes, different color profiles, different scenes, different types of photographs like photorealism, vintage, blah, blah, blah. You don't have, again, any storage issues. Your only storage is the generator that you're storing to sample from. Usually, all these models, especially for the open source ones, they don't have any usage restrictions, assuming that they themselves haven't been trained on sensitive data that they might leak during their generation process. And for the same reason, they are devoid of privacy issues. And the acquisition cost and noise is pretty low. The acquisition cost is low because you are not training the generator. It has been trained by for you by large corporations or research institutions. And the noise is fairly low as long as you can appropriately control the sampling process. So there are a lot of noisy data on the web, right? Like for example, I type an image of a dog, I get hot dog. Um, I mean, not what I wanted, even though it's not inaccurate. Um, or for example, I type image of a horse, I get a represent sketch of an engine because it's annotated by the metric horsepower. So uh, not all images on the web are true in terms of the accuracy to what we want from the prompt, or rather the subject in the prompt. And you might argue, let's just do clip filtering or some other kind of filtering. But again, all of this is extra work on top of already a super noisy data set. And that might drastically reduce the size of it. So there are pros and cons to it. So while generated data sort of serves as one axis of this work, the other axis is to move beyond this traditional ML paradigm, right? We have been seeing this quite often. You train a large model on a humongous amount of data once, and then like pray to God that it works in every scenario. um, Again, that is very falsified view of looking at how these models might be useful, because the world is dynamic, events keep happening, facts keep changing. So it is more plausible and sensible that we train a model that can take into account this drift, and can be continually trained on new data and deployed continually. So we want to move from the traditional single training paradigm to the continual learning paradigm. So our work heavily is inspired by this paper from last year from Oxford called Categories to Classify Name-Only Continual Learning by Exploring the Web. Um, in an essence, what it does is it uh, formalizes the standard continual learning, especially class incremental setup. If you have background in continual learning, there are a few setups like task incremental, domain incremental, and class incremental. This one is class incremental, which means at every instance in time, or at every task, as you say, you would see new classes in case of images, for example. And when they say name only, it means that they are only exposing the process to data which only consists of names of the classes at any given point of time. So, for example, at task t minus one, the input for them is just the two classes that they are concerned with, cats and dogs. And what they do is on the fly they scrape four different web search engines: Google, Bing, DuckDuckGo, and Flickr, obtain the images corresponding to these two concepts, and then simply take a pre-trained frozen encoder and train a linear head or a linear classifier on top of it, right? And then task T, they get two new classes, bears and ducks, do the same process, expand the linear probe, and train the linear probe. Okay, so uh, this paper, it sets up a foundation stone for research in this space of how to utilize generated data. How to utilize web data in continual learning. But the major drawback is it's sort of not truly continual, right? Like if you are familiar with continual learning, the whole point of continual learning is to avoid catastrophic forgetting. That happens because you train parameters that are like not in sync for every task. Like they might move, the weights might move in different direction for each task, which might have a conflicting nature to performance in the previous task that it might have seen. And the goal is to avoid that. The goal is to maintain stable performance across all the tasks, both seen before and both upcoming. So if you see over here, there are no updates happening to the backbone. It's frozen. So effectively, we mitigate any notion of forgetting here, and we are only training the linear probe and changing the linear probe at every task. So this makes it less continual and more just a normal incremental setting. Is there a question?
Yes, there seems to be a question. So I don't know if you would want to take that question now, or you would rather take that question at the end of the session, if that's okay with you.
I'll just take it now. So let's read it.
Okay,
F
fine.
is frozen when training task T. I cannot understand the benefit, only the classifier is trained. So the benefit rather is not about the way of training, but rather that can we use this dynamic on the fly web scraping to generate data or obtain data for continually training models. So their aim with this part over here, I don't know if you can see my cursor, or the model part is sort of not to disturb that. Like they can use any standard continual learning approach, like if you have EWC replay, dark experience replay, whatever that might be, you can use it. The main focus is just to see if we can do this dynamic crawling on the fly. And while I made it sound super naive and straightforward about the crawling process, which is just that they pass the name and get the images, it's not that naive. They do have some brevity in terms of the scraping and the post filtering that they apply, but I don't want to go into the details of that. If you want to know about that, feel free to look at the paper. But the reason I mentioned this frozen and the linear probe part is just to give you a argument about why I feel like this is not super continual learning esque, because you by definition, by design of this approach, you are mitigating most of the notion of forgetting that you would have, because the backbone is frozen. um task T is trained again by on the fly training of task T minus one's data. So this would just mean this is just a schematic. I believe in this case what they do is they obtain the images for the new classes, and for the older classes it just is a replay buffer. They don't do the same crawling again. But if you are training for very long enough, and even for the previous task new images would have been uploaded, then it might make sense to crawl. But again, it's very dependent on the scale of the time that you're training on. uh, so does that answer? Okay, cool. All right, let's go back in here. So one key drawback of all of these works is in my initial slides I had shown you about how people have been trying to incorporate generated data into the training process. However, the key drawback that I want to really emphasize is that they rely on a single generator, which is bad. Right, like we all know the nice things about ensembling and how well it can work, and you might have seen about model soups as well. So single model not good, multi models good, kind of. That's the bottom line, right? So again we ask the question, can we use multiple generators, like instead of like single generator sample all the examples, can we use more generators? It can be either generalized or specialized on certain concepts, and then some sample from them, the total set. And the answer is yes. And the reason I want to emphasize this is because these models, they are all trained on different data, they're all trained with different training budget, compute, training mechanism, and hence they incorporate different notions of representation for the same concepts. So if you look at here, for example, for the prompts that I have over here, which is a black and white image of a person highlighting dramatic contrast, uh, just look at deep flood IF versus SDXL, for example. Deep flood IF tends to generate more close up portraits, high contrast images, but SDXL, generates like a different uh, view of people for the same given prompt. Like it generates different postures, different background elements. So definitely for the same exact prompt, same exact concept, you can get very drastically different images out of different models, right? So, and at the end of the day, we want to maximize the diversity, right? So we should try to instead rely on more generators if we do have them, and we do have them, right? There are several uh, like high quality image generators available open source. So this is a main point that we start the work with. So, based on that, we construct a framework by trying to see whether we can use this approach, but instead of doing the scrolling, to do the generative process instead. Okay, so how does that look? So this is where I'll put a big asterisk. This framework is a legacy framework as of right now, because for the new version of the paper that we will be having, this has been changed quite substantially. The most basic outline of the framework still remains the same. However, certain elements of it has been changed and improved, but I won't disclose them right now. I'll just go over the stuff that we already have. So similar to the Oxford paper, we have multiple tasks over time. We get in these tasks only the names or the concepts. And when I say concepts, it can be anything, right? It can be just the names of the classes, it can be something more fine grained, it can be something more abstract. It's up to you. It's depending on what tasks you care about. So to keep it coherent with that paper, we use the same schematic. So you get dogs and cats, and then deers and bird. And in our case, we first pass this concept through a module called Psi, which is a prompt refiner module that takes the name of the concept and rewrites it to prompts which maximize diversity from a generator. Then we use these prompts to pass it through a generator denoted by italicized G. And the generators that we use in our case is DALI 2, STXL, CogView2, and DeepFlood. And then we obtain images from these generators using the prompts that we constructed. However, we do not arbitrarily use all of these images, because some images might be bad, some images might not be accurate, some images might be better to use than the other images. So we pass them through this delta module that is basically an ensembler, which we call as discover, which maximizes diversity and complexity of the training samples that we obtain from the generators, while keeping the training data budget constant. And then we use these images to finally train end to end, again super important, end to end, the full model, not only the linear head. So so that does mean that the notion of forgetting does exist quite evidently in our framework. I want to make sure that I make it clear that we do not devise a new continual learning method. In fact, our results are all utilizing existing continual learning methods that mitigate forgetting by design of it. For example, experience replay, dark experience replay, EWC. So we use those methods in conjunction with this framework to avoid forgetting. So the goal is not in this paper to show that we are worse or better at forgetting when we train with synthetic data, but more about what is the process to even begin with to utilizing synthetic data in continual learning. Okay, so what is this prompt refiner module? So this prompt refiner module basically takes the name of the concept, which is, for example, a dog, construct a base prompt out of it. The base prompt is basically the clip prompt, if you are familiar with that, which is an image of a class name. And then we pass that through Gemini recursively to generate meta prompt and prompt rewrites. So what are meta prompt and prompt rewrites? Meta prompt is basically 10 high level prompts that we get from the base prompt by rewriting them in different style by using Gemini. And then prompt rewrites are basically coarse rewritten versions of each of the meta prompts 5 different times. So in total, from one concept or one base prompt, we end with 50 total uh, prompts, which is the output of the prompt rewrites, and that is what we use. Again, the reason why we want to do this is because you can only generate so diverse images from a single prompt in a single concept in a single style. And because we know, like in deep learning 101, that the diversity of data dictates the model performance, we want to maximize diversity. So hence we want to have diverse prompts as well that we can use to obtain the samples from a generator. Why do we use Gemini? We test against GPT 3.5. The prompt rewrites that we obtained with Gemini has a lower average cosine embedding similarity. Sorry, embedding cosine similarity. What that means is you take each pair of prompts that were generated and just do pass it through a sentence transformer and obtain the cosine similarity of the embeddings. The lower it is, the more dissimilar the two prompts are, and the more dissimilar the prompts are, the more diverse it is, right? So in our case, Gemini is superior than 3.5 GPT, but yeah, GPT-4 must be superior. And in fact, in our newer versions where we have changed this prompt refiner module quite drastically, we use GPT-4, but for the version of the paper, Gemini is what we relied on. Just to visually show you the difference between meta prompt and prompt rewrite. So a meta prompt would be something like a photo of a person in earth tones. Then a prompt rewrite would be just rewritten versions, much more coarse, detailed of that meta prompt, like image of concept. Concept would be the person with a warm and inviting color palette, reminiscent of nature, using earth tones, for example, right? So you get the point. Okay, so the most important contribution of this work is the delta module, which is the ensembling module. And why do we call it Discover? Is because, as I said, it's an acronym for diversity and complexity ensembler, right? So we use sample complexity as a measure to measure the to estimate the contribution of each generator into our training data set. Okay, so this is probably the most interesting slide that you would see, um, if you are especially working in generative modeling. So last year at NeurIPS, there was a paper about sample complexity, and they introduced a new metric called relative Mahalanobis distance. If you are coming from OD detection background, then you might have heard this definition or term Mahalanobis distance quite commonly used. Um, so they constituted this metric to be a really good proxy to estimate sample complexity of images, especially training images. And what we did is we just investigated for the same concepts, what does the value, the RMD value, looks like for generators and different generated images. I'll explain what the metric is, but for now, just take it into account that lower the value of the metric or low RMD means that the simpler the images, high RMD, the more complex the images. So as you can see, certain images of the same concept like guitar. You can see here a low RMD image would be something like the guitar at the center of the image. There's hardly any occlusion, obstruction. It's a very smooth color profile, no perturbation or noise. And same goes for pretty much all the other concepts which are very low RMD. When you flip it to the high RMD regime, you can see things change, right? Like you have now a very different view of the guitar. You have more background elements, more texture, more infringement of the subject. So uh, you can certainly get more complex images, and these are all generated images, by the way. But the interesting part is, for the same concepts and the same prompts, if you look at different generators, especially the generators that we use, STXL, DALI 2, Diploid, and Cogview 2, they all tend to generate, on average, images of different complexity. This is super interesting to me personally, that they don't have a same coherent view of the world. Um, so, for example, take eyeglasses, for instance. SDXL on average generates much more complex images than that of the flood IF. But then you take candle on the flip side, then yeah, now the flood IF generates more complex examples than SDXL on average for the same prompts and the same concept. Some of this might be attributed to the randomness in the sampling process, but yeah, like the results are pretty significant, pretty consistent over multiple rounds of generation and under pretty similar hyperparameters. Um yeah, so this observation is quite conclusive. And this is not just the case with different generators, but also in different prompts. If you use different prompts, you from the same generator, you would get images of varying complexity. For example, a vintage photograph of concept with a warm faded aesthetic on average gives you a much higher average complexity of images than that of something like a black and white image of a concept highlighting dramatic contrast. So the variability is both on the axis of the prompts that you use and the generators that you use. So for example, you can have these are actual samples from our dataset where we know the RMD values. So you can have low RMD for dog, a minimalistic image of dog using clean line and muted colors, as compared to high RMD would be a photo of a dog in neutral tones. Okay, so I hope I sort of made this point pretty clear. Um, so finally, how are we using this sample complexity in our approach called Discover? Well, to recall what the RMD metric is, it's nothing but the Mahalanobis distance of the target sample to that of the class centroid, and subtracted from the from the data agnostic Mahalanobis distance to the data centroid itself from the target sample. That is basically what RMD is. So higher the RMD, more complex the image is. Lower the RMD, more simpler the image is. Okay, so how do we use this? So we construct a probabilistic measure of contribution, which we call Discover, that basically gives higher preference to images from generators that have on average higher RMD to be included in the training data set. That was a mouthful. What that means is that if I have a generator that on average gives me higher RMD samples, then those samples or that generator has a higher likelihood of contributing or being included in my final training set than the samples that have on average lower RMD values, right? So this is a probabilistic measure, which means that the probability associated to low RMD samples being included in the training dataset is non-zero, unlike a pure deterministic approach, which is pretty important, and I'll show you why. So why did we pick this probabilistic approach? If you had instead taken no multiple generator approach and relied only on stable diffusion XL, for instance, using the different prompts, this is the performance that you'll get. Just to highlight the performance over here, we have two domains, the in distribution and out of distribution, and for each we have two metrics, the area under the accuracy curve and the accuracy at the last point of training. So in both the metrics, the higher the better. So if you as I said, took only SDXL, no generator ensembling, then this is what you would get. But now if you introduce all the generators that we have and instead take equal weight ensemble, which means every generator contributes the same number of samples to my training set, then actually performance goes down as compared to only using SDXL. Quite unintuitive, right? But now, if you take a deterministic K highest RMD ensemble, which means you're slicing instead of it being a probabilistic approach, you're only taking the highest RMD examples, performance drastically improves, right? Which is good. So models do favor learning on more complex examples. Now take the opposite of that, take only the lowest RMD ensembles, performance takes a significant hit expected. And then if you take the inverse probability, which means that you give higher preference to lower RMD samples being included and lower preference to higher RMD samples being included, then this is what the performance is. And then finally, we come to our approach, which I explained in the previous slide. It gets the best performance. Now, it doesn't get like way higher in ID against K highest RMD ensemble, but in OD it does show statistically significant improvement. And this is the measure that we hence rely on for ensembling our generated data. So the takeaway from this work primarily is that our work is the first to demonstrate approach to ensemble generated data reliably, that does not rely on any handheld approach or manual annotation, but rather is very heuristic and probabilistic based. You can interpret this from a SVM perspective as well if you are very much into it. How this would look. This is not a actual factual diagram. This is not actually a data landscape. It's just a interpretation. So if you were to take only the K lowest RMD ensemble, so what does K lowest mean? Because RMD is a measure of Mandelbrot distance from the class prototype, the K lowest would mean that those are the samples that are super close to that of the class centroid, right? And so for that, it would mean it is more concentrated here, and for this class, it would mean it was more concentrated here. Now, if you were to only pick these samples for your training set and exclude, the farther away high RMD examples, the degree of freedom that you have to fit a linear classifier between the two that can create a perfectly separable boundary is quite a lot, right? I can draw n number of boundaries that can separate these two clusters. But in doing so, I might be misclassifying these high RMD examples because I don't see them during training, right? Now, instead, take um, discover, which includes higher number of high RMD examples. You now get a more tighter fit, which is more accurate as well. And in doing so, these samples sort of act like support vectors. If you're familiar with SVM, it just helps to construct the margin with highest separability. Okay, so now to the final part, which is results. So what we tested on? We tested on PAX, DomainNet, CIFAR10 warehouse. It's a more difficult data set of CIFAR10 and CCT. All of these have varied in distribution or in domain in distribution domains and out of distribution domains. And as I showed you before in the table, we measure the same two metrics across both of them. They have different number of classes and tasks, and number of classes per task for each of them depending on the configuration, and it's all class incremental setup. This is a huge table, but let me distill it for you. So basically what we have in this table is we test our approach in conjunction with common continual learning methods. As I said, continual learning suffers from the problem of catastrophic forgetting, and we have to mitigate it. And to mitigate it, there are already existing methods and papers that have developed techniques that can mitigate it to most extent, and those are these methods. So which is experience replay, ERMIR, dark experience replay plus plus, and all of these are existing papers. So we use them coupled with our approach of obtaining the training data for the process, and we compare to web scraping base prompt, which is just the clip prompt and image of a class name only obtained from stable diffusion excel, all the training images. Then we have diversified prompts, so we include all the prompts. Instead of only relying on base prompt, we include the prompt rewriting module. uh, but we still only generate from stxl. Then we do generative ensemble, which is discover basically. And then we have manually annotated. Just to let you know, all these options in the training data, they have the exact same training data budget, which means they have the exact same number of samples. So manually annotated sort of serves as the upper bound in domain, which is expected because it is constructed for that domain to do well on that test set of the domain. So as you can see, discover or gen ensemble in this case significantly outperforms every other option like web scraping, base prompt, and diversified prompt, both in ID and OD. Especially in OD, we get the most superior performance even over manually annotated. This is for PAX and DomainNet, and it also holds for CCT and CIFAR 10 as well. And it also holds with different backbones. So we tried with ResNet 18 and VITs. Results are pretty consistent and statistically significant over 5 runs. How does it scale? Going back to the question that I asked before, uh, pretty well. Not truly linear, like not true y equals to x linear, but it does have a positive scaling coefficient. So basically, as you keep increasing the size of the ensemble, which is the total number of samples that you have in the discover process, the performance keeps increasing. Um, so that is good. Uh, this is not very conclusive because this only relied on testing for ResNet 18 and VIT only on the PAX dataset up until 4x the data budget. We can continue extrapolating this beyond that if you want more accurate result. But yeah, just to show you the point that this does hold at least to a pretty big data range. So that is it. Thank you so much. I hope you found it interesting. And you had some takeaways out of it. If there's any questions, comments, feedback, you want to know more about the revised work that we are soon planning to release, happy to discuss them right now.
Thanks a lot, Diganta. I had quite an informative session with you. I'm sure I speak for everyone of us when we say that this paper is very interesting. It's a very interesting paper, and I'll probably go a bit deeper into the paper. I'll read it a bit deeper, and maybe we can work on some implementation. So I would like to know if anyone here has questions. Do we have questions?
Yeah, okay, let me read first this one, and then if
Yes.
anybody else has any question. If you want to
Yeah.
apply a modified version of your framework in the context of object detection, do you know any sort of good diffusion models which takes B boxes and category names to generate a scene? How do you imagine as problems that we can encounter in different parts of a method software? Oh yeah, yeah, super relevant. We only tried for image classification, as you can see. But as I said, this approach is agnostic to modality and task. For object detection, if you want to simply use B boxes, or you have coordinates of your B boxes, then you can use control net. So control net is basically, sort of as the name suggests, a controller for diffusion models, where you can add other semantic inputs on top of an image, or a prompt that you can use to modify. So for example, if your prompt is a cat sitting beside a dog in a park, and your control net can take an input where you provide sort of a sketch with the bounding boxes where the cat and the dog would be, instead of the image, just the bounding boxes, and it will generate within that. So you can use that. There are other models out there beyond control net that also have the capacity to take B boxes, or even edge maps, contours, any type of semantic input that you can think of. But yeah, we haven't tried it, but it's definitely something that would be interesting to see. Okay.
Okay. So I think that question is answered. I would like anyone else who has questions to present those questions. And in the meantime, I just want to mention, you said earlier, Diganta, that you were working on sort of an improved version of this project.
Yeah.
So I'm curious to know, apart from the other aspects you mentioned about the prompt generator, you had this defy block there that helped you refine your prompt and helped you refine and refine your rewrite your prompt. Yeah, good.
Hmm.
Yeah. So my question is, first of all, you use Gemini and
Hmm.
you compared Gemini to GPT 3.5.
Hmm.
Did you do any other comparisons? Were there any other LLMs that you compared?
No. No, but yeah, as I said, like for our revised version, we use GPT-4,
Okay.
and we do not. So for the revised version, pretty much everything is same except the prompt refiner module. That is the primary axis of change. So um, just a hint of what we do is we add a new feedback module to improve the rewriting process, and we do that through GPT-4. So the prompts are not as straightforwardly constructed as it was in this case. But yeah, like earlier we had only tried 3.5 and Gemini, but now we just defaulted to GPT-4.
Okay. So I have another question.
Yeah.
For this particular project now, you are working with images, but
Yeah.
I'm curious to see because, as you said, this project is modality agnostic. It doesn't really matter what modality you are actually working on. It's the
Mhm.
idea that counts. It works irrespective of modality. So I'm curious to know, do you have any intentions beyond this modified version that you're working on presently? Do you have any intentions of, say, switching to a different modality? Say perhaps you would like to apply this framework on video data. Any intentions towards that
Uh,
aspect?
well, does it sound interesting to me? Sure, but am I going to do it? Probably not. I only have so much time. I am not super familiar with other modalities as much as I am with images and certain aspects of language. So yeah, I would prefer if somebody takes inspiration from our work and does it. But yeah, I'm definitely quite intrigued by the possibilities, even if it is not exactly our approach or something that relates to our approach that can be used in other modalities. I think I was asked before this about the applications in biomedical sciences, where you can generate images of pathologies or x-rays, Yeah, so there are definitely applications and domains where it can be extended to, which we haven't tried. But yeah, I do not anticipate as of right now or in the near future that I'll be exploring those domains myself.
Okay. Okay. Thank you very much for elucidating on that. So, in the absence of any questions, I really want us to ask questions. Are we sure that there are no questions, please? If there are, please just signify. Very well then. In the absence of questions, then I would bring this session to a close. Thank you everybody for joining us this evening. Thank you for making the time out of your busy schedules to be with us here. And I would like to know if Digant would make his contact available so that we can all reach out to him if in the event that we have further questions. Perhaps we are experimenting and we need some kind of advice. We can all reach out to Digant. I would like that to be available. Yes, thank you. So Digant has made his email available here in the chat. I will also share it on the Discord channel so that we can reach out to him if we have any questions or we have any ideas. Once again, thank you everybody for being here. Thank you Digant, for taking the time out to walk us through your paper. Really appreciate that. And we wouldn't mind having another session with you at your convenience. Thank you very much.
Yep.
So, yeah, everyone.
I have a question, but it's
Okay.
not really related to this presentation. I just wanted to like get some of advice on what I'm doing in the vision space, and I was hoping maybe I could get some advice from and
Okay. You can reach out to me or Digant after the meeting. It would be available. It will be available.
Oh, okay.
Yeah.
Or bit and just ask the question, and then if he's available to answer.
Okay. Sure. Sure. So you can ask. You can ask.
Okay, so it's what I'm trying to do. I'm trying to change use generative models to change hairstyles and picture, and I'm not sure of the direction to take, which model backbone I should be working on. And so I've seen some people work on it where they change the face, but I just want to change the hairstyle of the person. Is there a direction you could point me into? So I have my data sets curated already and annotated, but I'm stuck at like the next phase. That's the modeling phase right now.
Okay. So it's very funny you ask this because in our last session, we had a researcher that presented his work similar to this. So the work that he presented in the last session dealt with localization and image transformation for 3D images, or rather for 3D point clouds, actually. So obviously, you are not dealing with 3D point clouds. You are dealing with two-dimensional images. But
Yeah.
I think that idea is also applicable here. The idea is modality agnostic, similar to what Diganta has discussed today. So I can share the paper to you, or I can send you the link to the session we had last week after the call. Just hit me up, and I'll send that to you.
I love that. Thank you so.
Yes. So
Uh,
my Discord handle is this. This is my Discord handle here. So you can just connect to me, and I'll send you the link to the recording. I'll send you the link to the paper as well. And
okay,
I think it will be applicable for you since you are doing localization. You are trying to localize a part of your image. Specifically, you are trying to localize a part of your image that contains the hairstyling, and then you are trying to edit that part of your image. That's exactly what we talked about in our meeting last week. It's just that instead of using images, he made use of 3D point clouds. So I think the idea would be applicable for you too. So that's a good place to start.
oh, okay. I'll reach out for you to share that with me. Thank you so much.
Yeah, you're welcome, brother. Yes.
Uh,
So in the absence of further questions, take care, everybody, and see you on our next meeting. Bye for now. Thanks a lot
bye.
again, Diganta. Thank you for making the time. Yeah.
Yep. Thank you. Bye.